This is a demonstration video about the current state of the nanocontroller system for flexible ultra-low power applications. For example, sensor and IoT nodes powered entirely by energy harvesting sources. The nanocontroller system has been developed at the Institute of Microelectronic Systems at Leibniz Universität Hannover and the Chair for Chip Design for Embedded Computing at TU Braunschweig. Recently, an evaluation ASIC has been successfully manufactured for silicon-proof validation, which will be demonstrated in this video. Before the demo starts, just a few words on the nanocontroller concept for energy-efficient nodes. The conventional widespread approach for IoT devices in home automation, etc., is to use a single general-purpose microcontroller for all system activities, as shown here. It is placed in the sleep mode and will wake up if processing application events is required. These events could be, for example, simple, frequent and short events like sensor value updates or system control decisions, as well as complex, infrequent events with a longer runtime and higher performance requirements, like wireless communication with other nodes or a base station. This approach shown here is a flexible and generic system approach in both hardware and software, which can be adapted to a majority of embedded applications. However, these advantages come with a drawback. The microcontroller is constantly powered in sleep mode to enable a frequent wake-up. The consumed leakage power in sleep mode can be quite high due to the full feature set of the general-purpose core and its large silicon area. In worst-case application scenarios, this power consumption can just be too high for very power-sensitive energy harvesting nodes, which aim at supplying themselves from environmental sources without using batteries. The proposed nanocontroller concept can minimize the continuous power consumption by combining the general-purpose microcontroller with a very small processor core, the nanocontroller. The nanocontroller is used for system control and simple task handling. The nanocontroller core is based on a minimal accumulator architecture shown in this simplified block diagram, yet it is fully programmable for flexible and intelligent use. Specifically, it is intended for processing the frequent, simple events in an application scenario. It features ultra-low power consumption, less than the sleep mode of the general-purpose microcontroller, for continuous, battery-less operation via energy harvesting. This is achieved because of a very compact, control flow-oriented 4-bit instruction set architecture to shrink the required power-consuming instruction memory to a minimum. However, I want to mention that the potential of the nanocontroller is not limited to control tasks only. The generic architecture can be extended by specialized units or coprocessors to support more sophisticated continuous processing. For example, in audio applications, microphone signal shaping and digital preprocessing for acoustic event classification. More information about projects using the nanocontroller can be found in the video description below. In a suitable application using the nanocontroller, the general-purpose core is only required for infrequent, complex events and can be power-gated completely by the power management. The core is switched on for processing the event, then for the rest of the time switched off again. The power gating can be under program control of the nanocontroller. To validate the nanocontroller concept in real hardware, a standard cell ASIC implementation of the system has been manufactured recently using a UMC 65 nanometer low leakage technology. The chip layout is shown here. Due to the very compact size of the nanocontroller, only a small region of the upper left die corner needs to be reserved and to be constantly active. Rest of the chip area is covered by the general-purpose microcontroller and its memory cells. Exactly that part of the system whose power is potentially shut down most of the time to reduce the power consumption to a minimum. This overlay shot of the die surface has been taken with a microscope camera on one of the manufactured die samples, clearly showing the project logo and the bonding pads. If you are curious about the large amount of memory and I/O pads shown here, this chip was fabricated for validation and demonstration purposes with debug interfaces. The integration, especially when it comes to the number of pin counts and functions, is not optimized for product end usage. And now for the demo part of this video. The application I want to demonstrate is an electronic door lock application, taken from one of our projects dealing with a processing platform for home automation, which is powered by multiple energy harvesting sources. As already mentioned, the Nanocontroller platform is flexible and versatile and can be used in other applications fields. Another project in progress that I want to mention here is about the auditory classification of masticatory events of ruminating and grazing cattle, where the nanocontroller is extended and used for continuous digital audio preprocessing and classification threshold detection. More information about this particular project can be found in the video description below. In the electronic door lock application, shown here, the nanocontroller is used for continuous proximity detection, which means detecting an electronic transponder keycard held to a door lock as an attempt to lock or unlock the door. If such a proximity event is detected because of a transponder card, the large general-purpose microcontroller will be supplied with power to communicate via RFID with the card, which is a complex processing task involving encryption. After readout, the microcontroller power domain will be switched off again. That is expected to happen only a few times a day, so that the high power consumption of the microcontroller core and RFID communication will not affect the average power consumption of the system, which is dominated by the energy-efficient nanocontroller. Let's have a look at the demo sequence now. The different parts of the demonstration setup are shown here. At first, we have got the ASIC. One sample is placed in the socket on the breakout board. The board is connected to the proximity sensor and RFID reader peripherals. The breakout board allows us to connect measurement equipment for both power domains, for the nanocontroller domain on the left side and for the big microcontroller domain on the right side. For this demo, I will use simple multimeters to show voltage and current of the domains. The development devices on the right side here are used to emulate the power and clock management, as these are not integrated on our digital domain evaluation ASIC. In the stage shown here, the nanocontroller is performing time of day updates and waiting for a proximity event, shown by the heartbeat LED here. With a clock setting of 6.25 MHz, a current of 18 microamperes is drawn at 1.2 volts, which corresponds to 22 microwatts and 3.6 microwatts per megahertz. The big microcontroller core is switched off to zero power. In case of a proximity event with a transponder card, the big core will be switched on by the nanocontroller to read the card, and this will be indicated by a small flash on a LED. After read, the big core signalizes that it can be switched off again, which will be also controlled by the nanocontroller. Let's see this. Proximity card. Core switched on, LED flash, and switched off again. The UART terminal connected for debugging on this notebook here indicates that information has been read out from the transponder card. I will do another readout to see this again watch the multimeters, and switched off again. The different stages have been rather quick here, but a separate analysis has shown that the dynamic power consumption of the big microcontroller core is 40 microwatts per megahertz. And due to the size of the big general purpose core and the integrated SRAM memories, the leakage power in sleep mode was 80 microwatts, which is about 3.6 times higher than that of the active nanocontroller power. In a single controller system, the leakage of the big core would be the continuous power consumption to provide the necessary functionality. And here, this shows the benefit of a very small nanocontroller for system control in this kind of application.